Welcome to This Explainer. Today, we're taking a fascinating chronological journey through one of the biggest shakeups in scientific history. We're going to explore exactly how physics shifted from viewing the entire universe as a highly predictable, perfectly ticking clock to a totally bizarre, mind-bending realm of probabilities. Let's jump right in.
Is the universe a predictable clock, or is it actually a cosmic slot machine? That question is really the heart of our explainer today. Because for centuries, we honestly thought we had reality all figured out. But what if our foundational understanding was just entirely incomplete? It's a huge idea that challenged the very foundation of how we understand reality. And as we'll see, this shift didn't just happen overnight.
Think about a classic billiard ball rolling across a pool table. It's macroscopic, it's predictable, and at any exact moment, you can know precisely where it is and exactly how fast it's going. Simple, right? But those comfortable, common-sense rules completely break down when we zoom way in and look at a subatomic particle, like an electron. An electron is wildly unpredictable. It actually exists as this strange hybrid mix of both a particle and a wave. So, to really appreciate the quantum revolution, we first have to establish exactly what it overthrew. We need to rewind to the golden age of classical physics. This was a purely causal, completely deterministic framework. Scientists genuinely believed that if you had complete knowledge of the past, you could perfectly compute the future. Basically, everything was knowable. Under the strict rules of Newton's universe, everything was strictly predictable. Particles, like our billiard ball, and waves, like ripples in a pond, were considered totally separate phenomena, doing their own separate routines. If you measured something, the outcome was absolutely guaranteed. Objects possessed well-defined variables like position and momentum at all times. Everything from an apple falling from a tree to an entire planet orbiting the sun just acted like a giant, mathematically elegant clock mechanism. Section 1. Cracks in the clockwork. The reluctant revolution of the early 1900s. At the turn of the 20th century, physicists started spotting anomalies at the subatomic scale that the old Newtonian clock just couldn't explain, and it is incredible how rapidly the resulting discoveries cascaded. In 1900, Max Planck introduced the idea of discrete packets of energy, which he called quanta. Just 5 years later, in 1905, Albert Einstein used photons to explain the photoelectric effect. Then Niels Bohr quantized the atom in 1913, and by 1923, Louis de Broglie dropped the bombshell hypothesis that particles could actually exhibit wave characteristics. Physics was literally scrambling to keep up, patching together what we now call the old quantum theory.
And you know what's wild? These pioneers weren't actually trying to destroy classical physics. Even Max Planck, the guy we consider the father of the quantum, was a super reluctant revolutionary. He famously said that he considered his quantum hypothesis just a mathematical trick to get the right answer. He didn't even initially believe his own theory represented actual physical reality. Crazy, right?
Section 2. The birth of modern theory. Forging a new mathematical reality.
By the mid-1920s, those old patchwork theories just weren't cutting it anymore, and a completely alien framework built out of advanced mathematics had to take over. Moving into 1925, we see this really accelerate. Werner Heisenberg developed matrix mechanics, and then the very next year, Erwin Schrödinger invented wave mechanics. These were independently created, but they turned out to be mathematically equivalent foundations for modern quantum mechanics. And by the time the Solvay Conference rolled around in 1927, this radical new physics was essentially solidified among the world's top scientific minds. The crucial paradigm shift here is just profound. Classical mechanics strictly insisted that physical entities were either particles or waves moving from point A to point B. But quantum mechanics stepped in and said, nope, all physical entities are actually hybrid particle waves. The absolute genius here is that they synthesized two completely separate classical concepts into one unified, magnificent framework known as wave-particle duality. Now, this mind-bending duality was famously demonstrated by the double-slit experiment. Picture this. You're firing electrons at a barrier that has two parallel slits. When the electrons hit the screen behind the barrier, they land as individual, discrete particles. But collectively over time, they build up an interference pattern, bright and dark bands exactly as if they were waves interfering with each other. But here's the absolute kicker. If you try to sneak a peek and put detectors at the slits to observe which one the electron actually passes through, the interference pattern completely disappears. It's like they know they're being watched. They act like waves until they're observed, at which point they just act like standard classical particles. And this brings us to a really devastating blow for classical predictability. Heisenberg's uncertainty principle formally dictates that no matter how carefully you arrange an experiment, it is impossible to have a precise prediction for a measurement of a particle's position and its momentum at the exact same time. The closer you get to pinning down one of those measurements, the less you can possibly know about the other. It literally proves that at a fundamental level, some things are just fundamentally unknowable before you measure them. So this fundamentally changes the game. Heavyweights like Max Born and Niels Bohr formalized this new reality in what became known as the Copenhagen interpretation. They boldly declared that the description of nature is essentially probabilistic. Even if you somehow had perfectly complete knowledge of the past, you could still only make probabilistic predictions about the future. That perfect deterministic clock completely shattered.
Section 3. The bizarre quantum reality, the measurement problem, and a very famous feline. Not all physicists were thrilled with this probabilistic slot machine universe, which leads us to the most famous critique in the history of science. In 1935, Erwin Schrödinger devised a famously diabolical step-by-step setup to bridge the microscopic quantum world with a macroscopic everyday object. Here is the scenario. You place a hypothetical cat in a sealed steel box. Then, you add a tiny amount of radioactive substance, so minuscule that it exists in a quantum state of maybe decaying, maybe not. You hook up a Geiger counter to detect any decay, which triggers a relay, which then drops a hammer, shattering your flask of deadly poison.
Okay, here is where it gets absolutely crazy. Because the cat's fate is entirely entangled with that single, unpredictable radioactive atom, the mathematics of the Copenhagen interpretation suggests something bizarre. According to the math, until that box is opened and a measurement is made, the cat actually exists in a superposition of being both dead and alive simultaneously. It is literally smeared between life and death until someone observes it.
Now, I want to be super clear about what you should take away from this. Schrödinger absolutely did not believe in zombie cats. He actually proposed this paradox as a reductio ad absurdum. He was intentionally trying to highlight how completely absurd the Copenhagen interpretation became when you tried to scale its rules up to macroscopic objects in the real world.
And honestly, he had a really great point. The paradox forces us to ask a pretty profound question. If atoms can happily exist in a superposition, why on earth don't we see macroscopic superpositions, like zombie cats, in our everyday lives? When exactly does a floating quantum possibility officially collapse into a single hard physical reality? This absolute head-scratcher is famously known as the measurement problem. Over the decades, a highly practical answer to this finally emerged, called decoherence. You see, the cat in the box isn't truly isolated from the universe. It is constantly bumping into air molecules, the heat, and the light bouncing around inside that space. According to modern physics, all of those environmental interactions act as tiny measurements. They instantly leak information out into the environment, destroying that delicate quantum superposition in a matter of nanoseconds. So, the environment effectively opens the box before we ever get the chance to. So, how do we make sense of this paradox today? Well, the debate is actually still going on. The Copenhagen camp says observation actively collapses the wave function. The many worlds interpretation argues that there is no collapse at all. The universe just constantly splits into parallel realities, one where the cat lives and one where it dies. But practically speaking, this isn't just a late-night philosophy debate anymore. In quantum computing today, we actually build ultra-isolated machines in extreme vacuums to intentionally prevent decoherence, purposely shielding and preserving these incredibly fragile superpositions, which we actually call cat states. As we continue to learn how to harness these bizarre quantum rules to power the advanced technologies of tomorrow, it leaves us staring right at the ultimate mystery of our universe. If our familiar, totally predictable macroscopic world is really just a dynamical pattern emerging from an unpredictable microscopic quantum soup, is reality ultimately governed by profound hidden harmony? Or are we just living on the outcome of a cosmic roll of the dice? Something to chew on as you go about the rest of your day.